Hey, AP Physics students, this is Mr. Everly talking to you. Um, Looking at our unit on circuits, it was a while ago. It was about, 3 weeks ago when we were just finishing up our unit on circuits, and then all this insanity happened. So I invite you to go back and take a look at some previous videos and some previous topics and see if you can review some of the things in this unit. One of the things that I did not cover in the videos that I provided was a major example on using Kirchoffs laws to write the equations for a particular circuit. That has happened on occasion on the AP test, and I'd like to do a little bit more in-depth example or a couple of examples of how this works. But first, a quick review of Kirchoffs laws. There's two of them. The first one is Kirchoff's loop rule. And the loop rule basically says that if you have any loop in a circuit, it doesn't have to be a one loop circuit. The circuit could have multiple paths. But as long as it's an entire loop, as you walk around the entire loop, you can write an equation so that all the voltage gains and drops add up to zero. So as we go around this circuit here, we start with the battery, and we can say the EMF of the battery minus the voltage drop of the resistor should equal zero, because that's the law of conservation of energy. As the current goes around the circuit, it gains energy here, loses energy here. The amount gained and the amount lost must be exactly the same. So there's a couple rules for writing this equation, though, you have to watch out for. The EMF rule says that if you move through the circuit, as you look around the circuit, as you walk around the circuit, and you do so in the direction of the EMF arrow. Okay, the EMF arrow is telling us which way the battery is pushing these imaginary little positive charges through the circuit. So the EMF arrow points from the negative side of the battery, the short side, to the positive side. If you move in a direction opposite the EMF arrow, you're going to make E, the EMF of the battery, negative. So you walk around this way, you make it positive. Walk around this way, you make it negative. The resistance rule. As we go around the circuit, if we move in the direction of the current, or the direction we think the current is in, you put into your equation minus IR. Okay, that's just Ohm's law, V equals IR. This is a negative because there's a drop in energy. Battery puts it in, resistor takes it out. If we move through the circuit in the direction opposite the current, we put a positive IRs because we're going from the low side to the high side. So moving in this direction indicates an increase in energy. Now, generally what we do is we try to go in the direction of the current, in the direction of the EMF arrow. It's not always possible, however, but in this really simple circuit, the equation I would write would be big E minus IR equals zero. And I come back to where I started. The junction rule. The junction rule just makes sense. The first one, the loop rule, is the law of conservation of energy. The junction rule is the law of conservation of charge. What it says is all the current going into a junction must equal all the current coming out of the junction. So looking at this little junction right here. A junction is where three or more wires come together and meet. If the current through this part of the circuit is I1, then it splits off into two, I2 and I3, then we could say that the equation would be I1 minus I2 minus I3 equals zero, which is just a fancy way of saying I1 equals I2 plus I3. However many electrons go into the junction must be the same as the number of electrons that leave the junction. And that's Kirchoff's junction rule. Okay, using Kirchoff's laws and rules, let's write the three equations for this particular circuit. So this is a relatively simple one compared to a few I've seen on the AP test, but Imagine we've got this battery EMF of E. We've got three resistors, R1, R2, and R3. We'd like to know how much current is flowing through each of the branches. And there's a number of ways to do it. One way is to set up the three equations. So the junction rule would say that, for example, at this junction, all the current going in must equal all the current coming out. Or another way of saying it is that I1 minus I2 minus I3 equals 0. So we have one equation. Unfortunately, that one equation has three unknowns. We've got the resistances, we have the EMF, we don't know what the currents are. So let's use the loop rule. We could say, imagine we go around one of these loops. You don't need the entire circuit, you just need a single loop. According to Kirchoffs' loop rule, E, because this is the direction of the EMF, the direction I'm walking through this loop, hit this guy, you'd say minus I1 R1. Come through here, you'd say minus I2 R2. We've come back to the battery. That's one legitimate equation. So now we have three unknowns, two equations. How are we going to get the third equation? We've got some options. We could use this loop. Okay, if we use that loop, we'd say E minus I1 R1, keep going around, minus I3 R3 equals 0. Now we've got three independent equations, three unknowns. This is solvable. Okay, it may not be fun, but it would be solvable. Another option, if you don't like this third equation, we could use this loop. Okay, so according to the loop rule, if we're moving in the direction of the current, this guy would be minus I3 R3. Keep going around. Now we're moving against the current. So I'm going to say plus I2 R2. Okay, so instead of one of these guys, we could use this equation. Now, since we only have three unknowns, we only need three equations. But these are four different, entirely independent equations we could write for this circuit. And then we'd solve them. Okay. All right, here's an example that's a little bit tougher. You can see it's kind of complicated. What we have here is a circuit with a couple of resistors, R1, big R1, and big R2. We've got three batteries, and not only do we have three batteries, the batteries all have some internal resistance, which we just treat like a separate resistor. Notice some of these batteries are fighting each other, some are helping each other. So this is kind of a complicated situation. And they want to know what's the current through each of the branches of the circuit. So imagine, starting over here, we've got current moving in this direction. This battery has got a pretty good size EMF, 15 volts. Let's say it's pushing current this way. Call it I1. It hits junction B here, and let's say it splits into I3 and I2. Okay, now if I'm right about this, we're forcing current in the opposite direction this battery is pushing. So I could be wrong about that. If I am, it's okay. In the calculations, I'll just get a negative number and say, oops, I guessed wrong about the direction of that current, but I have the right answer anyway. Okay. Now, we've got three unknowns here, I1, I2, and I3. So in order to solve for them, we need three equations. The easiest equation to write down is from the junction rule and say all the current going into junction B must equal all the current coming out of junction B. Or another way of saying it is I1 minus I2 minus I3 equals 0. Okay? Now, again, three unknowns, we need two more independent equations. So we have to use the loop rule. So I'm going to pick a loop and walk around it. So let's say I pick this loop here and go around in this direction. If I start here and work my way around this loop, the sum of all the potential gains and losses must add up to 0. So I'll start with E1. I'm moving in the direction of the EMF, so he's positive. Then I've got little r1 here. I'm moving in the direction of the current, so he's negative. Call it I1, little r1. Then we come around to this resistor, moving in the direction of the current, so I'm going to call it I1, big R1. Keep going. The current through this guy is I2, so I'm going to say minus I2, little r2. Now here, we're walking against the EMF direction. This battery pushes this way, so this is the high side of the battery, this is the low side of the battery, so this is a drop of E2. And then we're back around to our original spot, so there's our equation. I use this loop for my other equation. I could also use this loop too, but I got to pick one, so I'm going to pick this loop and say if I start here and go around this way, I'm in the direction of E2's EMF, so I'm going to say E2. Now I'm moving in the opposite direction of this guy's current, so I'm going to have to say plus I2, little r2, which is kind of weird, but keep going. Moving in the direction of that guy's current, so I'm going to say minus I3, r2. Moving in the direction of this guy's current, I'm going to say minus I3, r3, little r3. We're moving in the same direction of this guy's push, this EMF arrow. We're going to say plus E3. Now we're back around to where we started. So there's our equation. Okay. Now, in order to solve these things, it might be a good idea to do something we don't normally do, which is put the numbers into the equations. Okay. So just to make life a little bit simpler, this first equation is just going to be I1 minus I2 minus I3 equals 0. Second equation, put it here so you can see the givens. E1 is 15 volts, so I'm going to say 15 minus little r1 is 2 ohms, so I'm going to say minus 2I1. Big R1 is 4 ohms, so I'm going to say minus 4I1. Little r2 is 2 ohms, so I'm going to say minus 2I2. And then E2 is 6 volts, so I'm going to say minus 6 volts equals 0. Don't put units on it, just write 6. Okay, this guy, translate him into numbers. I've got E2, which is 6. Little r2 is 2, so I'm going to say plus 2I2. Big R2 is 3, so I'm going to say minus 3I3. Little r3 is 1, so I'm just going to say minus I3. And EMF 3 is 4 volts, so I'm going to say plus 4. Okay. So, to make this system of equations a little prettier, we'll say I1 minus I2 minus I3 equals 0. Here, let's bring together some like terms. 15 minus 6 is going to be 9. We got a pair of I1s, that's going to be minus 6I1 and minus 2I2. Okay, here we've got 10. Bring the I2s together, plus 2I2. Bring the I3s together, minus 4I3. Okay, now it turns out that they might just ask you to write 3 equations that could be solved for the currents in the circuit and ask you not to solve them. Write them, don't solve them. Boom, you're done. If they do ask you to solve them, you could put them into an equation solver. If you've got one of those on your calculator, you've got a system of equations here, 3 equations, 3 unknowns. It'll spit out the answers, and it is acceptable to do that on the AP test. If you don't have an equation solver and you want to do it the long way, you could do that. So maybe your next step would be to say, okay, I1 equals I2 plus I3. So looking at these equations, we could easily get rid of I1 here by replacing it with I2 plus I3. So I'll say minus 6I2 minus 6I3 minus 2I2 equals 0. So if I simplify that equation, I'm going to get 9 minus 6I2 minus, 8I2 minus 6I3 equals 0. So now I've got 2 equations and 2 unknowns because this guy graduates over here. This guy got turned into this one when we substituted in I2 plus I3 for I1. And so let me finish this off. Okay, so now we've got a set of 2 equations with 2 unknowns, so that's a little bit easier to solve. Maybe what we could do is multiply this equation by 4 and then add the 2 equations up, because when I multiply this equation by 4, this term will become a positive 8, and when I add them up, I'm going to lose the I2s. So let's give that a shot. So my system of equations will now be okay, just graduated this guy to here. This guy gets multiplied by 4, so I'm going to call this 40 plus 8I2 minus 16I3. When I do that, I've got 49. I add these 2 guys up, add these 2 guys up, I get 0. Add these 2 guys up, I get 22. Okay, so what does that mean? It means I3 is equal to 49/22. Let's see. Punch that out, and it turns out to be 2.23. Okay. All right, next step, find I2. I guess we could just pick one of these equations up here. So if I grab this equation, I could say that negative 8I2 equals 6I3 minus 9. I know, so let's divide both sides by negative 8, get rid of that. So I know now that I2 is 6 times 2.23 minus 9 divided by negative 8. Punch that out and we should get negative 0.545. Okay. And then lastly, I think we could jump right up here and come up with a value for I1. I1 is just I2 plus I3. So since we know what I3 is and we know what I2 is, we add them up and we get 1.68. And we've got this thing solved. We know the currents through each of the branches. So pretty crazy problem, and one that you may have to solve, you may not have to solve, but in any case you should be able to use Kirchoffs laws to come up with the correct number of independent equations to solve just about any circuit problem.